Hi, can you hear me? Yeah. Awesome. So I'm gonna not talk about that much about Solidity in this talk, but the talk is, it uses Solidity, so hopefully you'll still find some value in this talk. Yeah, my name is Chandra, and I work at Certora as a research scientist. And today I'm going to talk about mutation testing, which is a technique for systematically introducing bugs in your code so that you can evaluate and assess the quality of a specification or a test suite. Okay, so I think I don't really need to motivate this for this audience that much. So DeFi is really getting it's more and more important every day, and a lot of really critical applications that involve financial transactions all rely on DeFi applications. So it actually makes it really important to have certain correctness guarantees of these kinds of applications. And unfortunately, there are often lots of vulnerabilities in these applications that continue to be exploited. So naturally, in the past couple of years, many tools and techniques have been proposed that are using a variety of different approaches for formally verifying, which it's a pretty wide term at this point. Some people are using fuzzing, some people are using a bounded model checking, symbolic execution, like more rigorous theorem proving style things, and these are becoming more and more popular. So what do these techniques actually do? These techniques provide strong mathematical guarantees about the correctness of your code. And so often, they actually tell you whether, it gives you a guarantee that there is no bug in your program at all. So you don't have to worry about fixing or adding more tests later on in your, to find those kinds of bugs. Okay, so just to give you a quick high-level overview of what I mean by formal verification. So the idea is that you have some code, and so in this case, we have some contracts that are written in a language like Solidity, and you have some specification. So the specification is usually a high-level functional correctness property that you want your code to satisfy. And so in this talk, I'm going to mostly focus on the Certora Prover, which is the tool that we've built for checking these kinds of high-level functional properties about your code. Okay, so basically we have this language called CVL. It just stands for Certora Verification Language. We weren't really very creative about the names here. But the idea is that you take your code and you take your spec and you pass it to the prover, and the prover basically tells you whether your code matches the specification, which is what you want, or if there's a counterexample and you get a violation. Okay, so this is actually great, and it's we have seen some success already, not just from Certora, but also from a lot of other really interesting tools. However, if you're a critic of formal verification, you could say that, well, formal verification is just guaranteeing that your code has the same bugs as your spec. So if you do think that, then I will kind of agree with you. And in fact, I'll go further, and I'll say that formal verification guarantees that your code only has the same bugs as your spec. Now, why am I actually thinking about formal verification through this lens? The reason is because formal verification relies on the completeness and the correctness of the spec itself, right? So it is actually really important to carefully think about how well your specification is capturing the intention that you have. So most of the time when you're writing these specs, at least in the first attempt, you're not actually going to get a complete specification. It's really hard. In fact, even if you keep trying, you're not going to really get a full complete specification. That's quite challenging as a task. And not only that, sometimes even if you are really careful and you have thought about all the properties that your code should satisfy, it turns out that we are humans and we can make mistakes, and so you might just have a little bug in your specification. And so what does formal verification do in that situation? Well, formal verification will just check that your code also has the same bug that you have accidentally introduced in your spec. So what do we do in this situation? Like, is there a way to make sure that our specification doesn't have small issues or is not complete, or is just missing some properties that are relevant to your program? And the answer is yes, and that's what this talk is going to be about. So before I actually go into the answer itself, I want to give you a very quick example of a program, and we're going to go through this program and use this program for the rest of the talk to understand what this idea is. Okay, so here we have a contract. This is the Solidity code, and the name of the contract is Borda. So I don't know how many of you actually have heard of this this mechanism. So it's a voting mechanism. It's pretty simple actually. So I'm just going to quickly walk through the code and just give you a quick overview of what's really happening. This is actually not the entire program. This is just a little snippet from the entire code. So we have this method called vote, and vote basically takes 3 addresses, first, second, third, and it has some requires. So first require says that the message sender should not have already voted, and the second require says that the first, second, third addresses should all be different. Okay, so then once we have those requires, we basically just set the value of the voted field for message sender. So voted is an array, and so we set the value for message sender to be true. And then we cast the vote. So the first address gets a vote 3, the second one gets 2, and so on. And finally, we have this voted function, which is just a view function. And this is just going to return the status of a given address X. Okay, so what are some properties that you would like for this program to satisfy? So I have some here, and if you have some that you can think of, feel free to raise your hand and share them with me. So one property that could be useful is that every user should only vote once. Another property that is relevant is that the points for the candidates should be correctly tallied up, right? So we don't want to have any mistakes in computing the score of the different the candidates. Similarly, we also want to make sure that the winner has the most number of points. That's an obvious one. A subtle one is that the order in which you vote should not actually affect the result of the vote, right? So if you put a vote for the second address first and the first address last, that should not affect who wins the vote. And finally, I have another one, which is that everybody should be allowed to vote. So if you have not cast a vote so far, you should be able to vote, and no other address should be able to prevent you from voting. Are there any other ideas people have? Okay, we'll go through some others in just a little bit. Okay, so we have all these properties. Now the question is, are these properties sufficient? And even if they are sufficient, are they all correctly formalized? And to answer these kinds of questions, we are proposing this technique of mutation testing. So what is mutation testing? It's a technique that the software engineering community has been studying for several years now. And the idea is pretty simple. You systematically introduce bugs in the program, and typically you do this automatically, and you check whether your test suite catches the bug or not. And so in this talk, we are going to use mutation testing in the context of formal verification. So instead of testing the efficacy of a test suite, we are going to test the efficacy of a specification. And so we have built this tool called Gambit. It's a mutation generation tool, and it is basically targets Solidity programs, and it generates mutations for you. And it's open source, so you can check it out at that link. It's also implemented in Rust, and that actually has some hopefully nice consequences that I'm going to talk about later in this presentation. Okay, so how does Gambit work? So the key idea here is we generate mutants and then we verify them. So we start with one Solidity file, and we call Gambit, and we generate a bunch of variations of that file. And the important thing here is that Gambit is a first-order mutant generator. So what does that mean? It means that every mutant that Gambit generates has one change and one change only. So it's not doing any compound mutations or anything like that. And this is actually a design decision that we deliberately decided upon, because there is quite a bit of research in mutation testing that shows that if you have higher order mutants, they're actually not that much better in like exposing loopholes in your tests or specifications. So what it does, though, on the other hand, it kind of makes it harder to realize what exactly in your mutant actually is causing the specification to pass the test or pass the verification. So we decided that instead of going for higher order mutations, we're just going to stick to first order mutations. But this is a decision that can be easily changed. It's just it doesn't actually change necessarily the way the tool works. Okay, so now that we have generated a bunch of mutants, the next step is to verify them. So we have, within Certora, we have essentially, we have an integration of Gambit with our verification tool, which is the Certora Prover. And so what we do is each of the mutants that Gambit produces, we then take the specification for the original program, and we basically just run the verifier on each of those mutants. And so what this tells us is that, so one thing that I should emphasize here is the specification is actually not changing. So we are using the same specification for all the mutants. We can actually have a discussion about whether it makes sense to change the specification. It's actually something we have thought about, but for now, we are basically just not changing the specification at all, only mutating the Solidity programs. Okay, so essentially, we have all these mutants, which are basically just new Solidity files for the given input Solidity file, and we are just verifying them against the same spec. So two things can happen. Either the mutant passes verification, and this is bad. So if the mutant passes verification, that means that there is a loophole or a gap in the spec. And often what happens is we look at the mutant and we try to figure out why the mutant passes, and then we add more properties or rules to our specification. The other outcome is that the mutant fails verification. So this is good. So we want our mutants to fail verification because that means that our spec is doing a good job of catching buggy versions. Okay, so going back to that, the Borda example that I showed in the beginning, so remember we had these 5 properties that I talked about, and it turned out that those properties were actually not sufficient. So here's a concrete mutant that Gambit produced. So here, the change is actually very simple, right? So in the beginning, we had voted of message sender was set to true, and Gambit just changed it to false. And it turns out that none of these properties that we have here are good enough to catch this mutant. So this is bad, because that means that the same person can vote multiple times. So what do we do in this case? So we just add a new property, right? So in this case, the property that we added is that if you vote, so vote of first, second, third, right? That should imply that the status of the voted status of the message sender should be set to true. And so I'm just writing it in logic, but we basically implemented this in the CVL, the Certora verification language, and we found that once we added this extra property, this mutant was caught, right? So the verification failed, which is what we want. Okay, so we have been working on Gambit for the past year and a half at this point, and we have been using it very extensively within Certora. And I'm going to talk about exactly how we use it in a little bit. But one thing that working with Gambit has done is it has shown us a few ways in which a specification can have problems. So the first way is basically what we just saw, right? So you didn't even think about a property, right? So you, it's just a major gap in the spec, and there was no way to fix existing properties. You just have to come up with a new way to check the contract. Another thing that happens is maybe you actually do have a property, but you didn't, you missed some kind of logical expression in it. So maybe you missed a clause or something. And this is also something that happens quite often. And we have seen this when we verify customer projects. And we just basically add to an existing property. And so the property could be an invariant, or it could be a rule, or anything else. Okay, so the third way is the kind of the silly way, but unfortunately this is also the most common way. So this is just human error, right? You have a property in your mind, you thought you did a good job of translating that to logic, turns out you didn't, and your verification just goes through, but it shouldn't. So these are the 3 ways in which we have so far seen specifications to have gaps, and all of these are pretty easy to catch with a technique like mutation testing. So another thing that we have done, so as I said earlier, we have integrated Gambit with the Certura approver. And so it is kind of part of the workflow. So when we do verification of customer projects, we are running Gambit pretty regularly during the pipeline just to see how good the specification is doing. And so one of the things that we have as part of this pipeline is this visualization. I just want to go through it real quick and show you what this means. You can click on that QR code if you're interested. I will say that it's actually not meant to be viewed on a phone. So if you can view it on a laptop, that would be better. It will render on the phone fine. Well, not fine. It'll render, but it won't look very good. Okay, so what's exactly happening in this visualization? So we have these green circles, and we have these gray dots. So the green circles are representing properties or specifications that you have written. So for the purpose of the Certura approver, each of those actually just represent some rule or some invariant. That's just, it's a little bit of a Certura specific thing, but you can just think of it as any high-level specification of your program. And you have these gray dots. The gray dots are the mutants. So if a gray dot is inside a green circle, that means that the property that is being represented by the green circle is catching the mutant. So if you have lots of gray dots inside a circle, that means that circle is catching a lot of mutants. Okay, we provide a few other additional information here. So one of the things is coverage. If you maybe have heard of the term mutation score, that's just another word for coverage. Basically, it just tells you how many mutants were killed. This is a little bit of I should say, you should take this with a grain of salt, because when you compute the coverage, you should take into account whether the mutants are semantically equivalent to the original program. And this is something we don't actually do right now with Gambit, but we are interested in coming up with techniques to check the equivalence of these mutants. And we also have some ideas for how to do it. Another thing that we show here is this idea called solo rule. This is a little bit tricky because I actually really like this metric. So what solo rule tells you is how good is a rule. And the way it does that is basically it counts the number of mutants that are caught by only one rule. And why is that good? Because it actually tells you whether there is any correlation between two properties, right? So when you're writing specifications, sometimes what can happen is maybe you wrote two different properties, but they're kind of checking the same thing. And that's not really useful. So you want to have a way to check whether two rules or two properties have any overlapping behavior, right? So the solo rule is kind of a proxy for measuring that kind of thing. Some of the other things, so on the left, we also show you the successful rules. So a rule is successful if it is at least catching one mutant. A rule is unsuccessful if it catches no mutant. And so often what we do is we kind of, we think about why some of these rules are unsuccessful, and this actually gives us a way to either fix the rules or just get rid of them, right? Verification is already pretty expensive, so we don't want to run verification on rules that are not doing anything interesting. A few more things we do is we show you a diff of the mutants, and we also just give you all the mutants as patches, and you can click through them, you can look at them, and so on. Am I already done? Oh, I have 5 more minutes. Okay, great. I'll hurry up. Okay, so how are we using this at Certura? Like I said, one of the things we do is as we write specs for customer projects, we continuously use Gambit to generate mutants, and then we try to see if the spec has loopholes, and then we improve the spec. And also at the end, we generate the kind of the report I showed you just to give an idea to the community or the user about the results of the verification. Another use case, and I actually talked about this at the TrustX workshop earlier this week, is we use Gambit for evaluating spec bounty competitions. And this is quite interesting because if you are doing these contests where the community is writing specifications, how do you evaluate them? How do you know if a spec is good and how does it compare to other specs? So we have found that Gambit actually is a pretty good way to measure or evaluate specifications with respect to each other. Another thing that we have done, so far I showed you how we are using Gambit within the Citra approver, but we have also started working on using it with other tools. And in one in particular that we did recently is we integrated the Gambit with this ERCX test suite. So it's not just useful for specification, you can also use it for evaluating tests. ERCX is a test suite that's developed by Runtime Verification. And one of the things that we found by running Gambit is that even though the test suite was actually pretty good to begin with, they still had missing tests. And so we added 5 more tests. We also discovered some interesting correlation between the tests. So this is kind of similar to the solo rules idea. And we were able to actually minimize the test suite significantly. So here I have a very, like a little graph that shows you how we were able to reduce the size of the test suite and how that affected the running time of the test suite. But also we made sure that it doesn't actually lose coverage. So we don't want to sacrifice coverage, but we do want to make sure that if possible, the test suite is as minimal as possible. Another quick result here is we then ran the minimized test suite on known buggy ERC20s, and we found that we were able to catch all the bugs, but the test suite was running faster, which was kind of the hope. Okay, so really quickly, how does Gambit actually work? So as I said in the beginning, so far it only works on Solidity programs. This whole box is Gambit. So Gambit first calls the Solidity compiler. It generates the JSON AST, and the JSON AST is passed to the mutator module. The mutator basically has a thin wrapper around the AST data structure, and it is responsible for generating all the mutants. I'm going to talk very quickly about what those mutants are. And finally, we have this filter and validate mechanism. So Gambit, by default, is going to find all the possible mutants it can. Sometimes maybe you need fewer than that, so you can filter them out. And Gambit will also actually make sure that the mutants compile. So it calls the Solidity compiler on all the mutants and then filters out the ones that don't compile. Okay, and then the last step is the mutant writer. So this is basically going to take all the mutants and write them to disk, and it produces some interesting pieces of information. It produces a log. It produces some metadata about the mutants that we later use when we are doing verification of the mutants. So these are so far the mutants that we support. We actually have a few others that are kind of experimental at the moment. We ended up disabling some of them because they were sometimes producing mutants that we didn't find very interesting. If you have ideas, I would love to accept a PR. This tool is open source, so feel free to check it out, and I would love if people contribute to it. One last thing is Gambit also has a very useful configuration language. So you can use the tool from the CLI, but we found that for complex protocols and like complex Solidity projects, sometimes the CLI gets too messy. So we built this simple configuration language, and what this lets you do is you can actually localize the mutants to some contracts and some functions only. You can also choose what mutations you want to do, and you can also pass in various Solidity compiler flags, because those are actually required for running the compiler and generating the AST and also validating the mutants that we generate. So yeah, that was Gambit. So it's a tool for automatically generating mutants, and we have integrated it with the Citra approver, and we have also used it with a testing framework called ERCX. Coming soon is an integration of Gambit with Foundry, and this is where the fact that it's implemented in Rust, I hope will be useful, because Foundry is also in Rust. And I've been talking about doing it for a while, and I think we finally have the bandwidth and a person who can help me do this. So yeah, that was it. I presented mutation testing, which is a technique for introducing bugs in your code so that you can use the bugs to check the efficacy of a test suite or a specification in our case. And the tool we built is Gambit. Check it out. There's documentation that can be improved. There's also the repository, which is open source. And yeah, if you have questions, I'll happily take them.
Thank you so much. I see some hands up already, so let's take some questions.
First of all, I'd like to say thank you very much. It was very clear. It was very explicit. It's understandable. I have a twofold question. With regards to mutation testing picking up, my first question is, how does Gambit differ from another mutation testing framework like Vertigo, like they're focusing at the prototype? Yeah. The other question, which probably is on other people's mind, is if the functional language is Rust, then how would it work with other test specifications, for example, that are not using Rust for the long term? For the short term, obviously, Foundry works very well with Rust. But say, for example, somebody uses TypeScript as another platform. So what I'm asking is, would Gambit be robust enough to deal with another testing suite that is written on, for example, like another language?
Okay, so the first question was, how does it compare to Vertigo and Universal Mutator and all these other tools? So it is actually similar to Vertigo in many ways. In fact, there were a couple of other mutation testing tools that we looked at before building this. Vertigo is one of them. There's the Universal Mutator, and there's another one called Sumo. The main difference is we are kind of guided more by the AST than a lot of these other tools are. So we are trying to generate as few invalid mutants as possible by using the AST information that the Solidity compiler provides. The second question was, how easy would it be to integrate Gambit with other tools? Is that the question? So not that hard. I mean, you're going to have to shell out to Gambit one way or the other. For Foundry, I think maybe we don't have to shell out because we can just call Gambit, right? But for Certora Prover, we actually shell out because Prover is implemented in Kotlin, and we basically just call out to the Gambit binary.
Okay, any more questions for Chandra? Yes, there's one.
Hi, yeah, super interesting. I mean, this is more tongue-in-cheek, but still, ostensibly, I could start with an empty source code, take the mutator, right, and mutate until I synthesize the specification. So I could try to use it as a form of functional synthesis, and not the most efficient one, I would say. But I mean, have you thought of doing that? Like, you could even try to do some kind of program repair using this, maybe.
So that's actually a pretty interesting point. I have been thinking about this for a while. Like, what if we just start with the simplest spec? So we have like, in the prover, we have this sanity spec where all we do is we just assert true or something, or we just do a reachability check or something. And that doesn't actually check any property, and it basically just gives you something to start with, which is very basic, and you can just do mutations to generate to guide the generation of the spec. One downside I will say is, I think that unless we somehow improve the kinds of mutations we're generating in a dramatic way, the properties that you write when you're just guided by mutations are different than what you would otherwise write. Like, people mostly end up writing these unit testing properties. That's what we call them. They're basically like tests, but just generalized, right? So we do want to make sure that we don't just do that, or if we do, then we should improve Gambit significantly so that it does more fancy mutations.
Okay, thank you, Chandra. Big round of applause, please.